my name is Laura Alford, continuing our series on hydrostatics. This lecture is going to be on pressure and buoyancy. So pressure and buoyancy are two key concepts of hydrostatics, worthy of their own lecture, I thought. So that's what this one is aimed at here. First, the definition. So here is hydrostatic pressure. Hydrostatic pressure, we're going to denote P sub 0. It's defined as the density of water times gravity times H, which is the depth. So you can see it's a linear relationship between the pressure and the depth. It's measured from the free surface, which means that it's gauge pressure. We're not considering atmospheric pressure on top of this. Now, a fluid acts on an object via the pressure P. So like I said, just a general body here can be anything. Pressure acts all around it. Remember that pressure is a scalar quantity. It's just a number, right? It doesn't have any direction to it yet. It's not until it encounters an object and it acts normal to its surface that you actually get a direction and a resulting force from that. Okay. You might have run into Archimedes' principle before. Hopefully in high school or something like that. All it really means is that the buoyancy of an object or buoyant force is equal to the density of the fluid that it's in times gravity times the volume of the displaced fluid. So you take any object and stick it in the water, however much water it displaces, not necessarily its volume, but how much it displaces. Multiply that by the density of water, in this case gravity, you get the total buoyant force that's acting on this body. Obviously, the buoyant force is very much dependent on how much volume is in the water, right? So here's an illustration. The body here in the first one is completely underwater, so it has the greatest buoyant force that's acting on it. If you were to take up this body or this rock and slowly lift it up out of the water, and it would have less and less buoyancy as you go along, right? So this just illustrating exactly the kind of the relationship between buoyancy and the underwater volume here. For a ship, it's the same thing, right? So this is sort of like a cross-section of a ship. The ship has a given underwater volume here. Again, it's represented by this triangle, this Naval symbol here. The total buoyant force is just going to be equal to the density of water that it's in times gravity times the underwater volume. No matter how complicated the ship is, right, how complicated the hull is, if you can get the volume, you know the total buoyant force here. Okay. Just a note on the density of water, right? If you're in the ocean, you're in salt water. If you are in the Great Lakes or on a river, you're in fresh water. And even though it doesn't look like these numbers change that much, it does make a difference. If you were in a ship and you were in the ocean, like in salt water, and you drove up into a river, then the density of the water would change, and you would actually lose some draft because the density of salt water is greater, so it can give more of a buoyant force. So if you are designing a ship that's going to be transitioning between these two, you need to make sure that you design it such that the draft can handle this change just due to the density of the water. Okay, so a related concept to this is now we're going to talk about static equilibrium. Static equilibrium has two conditions that need to be met. The first is that the total amount of force, the forces need to equal 0. In general, for the case of ships, it means that the total buoyant force is equal to the weight of the ship. The second condition is a little bit trickier. It means that the sum of the moments equals 0, and I'll explain what I mean by that. So condition 1, right, here is a ship. It sits in the water. When the buoyant force is equal to the weight of the ship, then it is at rest, and it has a given draft T. Okay, that one's easy. To look at condition 2, now we need a little bit more information. The weight of the ship acts through the center of gravity, denoted here G. The center of buoyancy is the center point where all of the buoyant force is considered to act. So that's B here. If G and B are aligned vertically, it means that there are no moments and the second condition is met, the ship is in static equilibrium. If the ship is tipped, something comes along, the G and B are not aligned vertically, the forces now induce a moment, and so now it is no longer in static equilibrium. But ships like to be in static equilibrium, so they will try to get back to this condition here. So example here, again, with some simple blocks, right? It can be a ship, it can be as simple as these blocks, right? It doesn't matter how close or how far away G and B are. As long as they are aligned vertically, they are in static equilibrium. Okay. For a ship here, okay, so going back, we have G and B when it's in static equilibrium. G and B will be aligned on the center line of the ship, almost always. Where the center line of the ship intersects the keel, we're going to call that a new point, K, because we'll use that in the next lecture. This assumes port and starboard symmetry with the ship, which is generally the case, so you're pretty safe there. But unfortunately, static equilibrium, all well and good, right? Good to have your ship in equilibrium, but it's not enough. I mean, as we saw before with the ship when it gets tipped over a little bit, what happens to the ship? Does it continue flipping over, or does it come back to upright, come back to static equilibrium? That is the study of stability, and that's what we're going to talk about in the next lecture. So thank you very much for watching, and see you next time.